Very good morning. Welcome you all to this NPTEL course on Economic Operation and Control of Power Systems. And today we'll have lecture 3, that is Control in Power Systems. As you know, that the important aspect of power system is control engineering, where we need to control the power outputs, and also in specific to automatic generation control, we are expected to restore the system frequency when it deviates from either 50 or 60 Hz. It is also important to relocate generation to keep it at economic dispatch point. Also keep interchange with other control areas as scheduled megawatts. Monitor and control generators as they ramp up and ramp down. So if you see, the power system is a very dynamic one, which has to increase its power output sometimes, it has to reduce its power output sometimes, and then you are supposed to transmit X megawatt of power from one area to other area. And then the economic operating point, which is, let's say, X megawatt, that has to be generated at that given point of time. And the frequency need to be very close to 50 or 60 Hertz always. Though it is next to impossible to achieve exactly 50 or 60 all the time, but the attempt to have it same, because if you can have the same frequency throughout the day, then your system becomes very big. Now, first of all, try to understand the basic turbine generator mechanism, what exactly happens. So as you could see, there is a rotating device where you give mechanical energy, and the turbine actually rotates, and that drives your generator, and then you have electrical energy as an output. Now, frequency is directly related to the speed of rotation. So whenever there is a rotating device, then you have frequency. So the frequency becomes constant when the rotation becomes constant. Now similarly, it is also expected that the mechanical energy and the electrical energy output, they must be equal. Whatever the mechanical energy you provide, it is expected to deliver same amount of electrical energy with different forms. So the mechanical torque, which is very important factor, which is negative of electrical torque, then the speed remain constant. So you could see the direction of rotation of the turbine and the generator, they are opposite to each other, so negative to each other. Okay. Electrical load changes are uncontrolled because we consumers behave differently. So no one can control the load to a particular value. So the load has to oscillate every second, every millisecond. So they are uncontrollable. So we must control the mechanical energy input to match. Very interesting. So now what is happening? The electrical energy requirement is keep on oscillating. So we cannot make it constant because it is impossible, because it depends on many customers' behavior. However, the mechanical energy input that we are providing to generate electricity, that need to be controlled as per the variation being seen through my electrical energy requirement. So that is the challenge. So for that, we need to have control mechanisms to control your operation. And you could see that there is a general control system which receives many signals from different corridors. That is, signals through turbine generating unit, and if you have many turbine generator units, then each and every turbine generator unit must communicate to your generation control systems. And you must be also having tie line power flow to neighboring system. For an example, let's say there is a power transmission between Uttarakhand to Rajasthan. Okay, so if there is an agreement that this amount of power has to be exchanged, so probably you have to make sure that all the time the tie line flow is as per your desired commitment. Okay, so that is another interesting point. And then you have to measure the generator electrical output. You have to measure the generator, system frequency, and also you need to measure the neighboring output. So all those signals we have to collect and then give to your generator control system every second or every millisecond. Now, let us get into the mathematics of it. Now, when you try to carry out mathematical analysis of a generation control, what exactly happens that the I alpha, which is the net torque, and the M, which is omega I. I will explain you the variables slowly. So the P net, net power, which is omega T net, the torque net, which is omega times I alpha, because T equal to I alpha, and which is nothing but my M alpha, because omega I equal to M. So what is omega, which is rotational speed, alpha is rotational acceleration, delta phase angle of rotating machine, T net is the net accelerating torque in the machine, T mechanical is the mechanical torque exerted on the machine by the turbine, T electrical is the electrical torque exerted on the machine by the generator, and P net is the net accelerating power. And similarly, P mechanical, which is mechanical power output, and P electrical is the electrical power output. And I is very well known moment of inertia, M is the angular momentum of the machine. So these are the standard basic background, and based on which we will try to develop some of the important equations in due course of time. Now, if I have to model a generator, because generator is a physical device, okay, and that generator need to be modeled mathematically. So what happens in a generator? We give mechanical energy, all right, and there is a negative feedback signal which is coming from the change in electrical signal. So what is happening? We detect the change in electrical power requirement, and hence we change our mechanical power input so that the delta omega will be as per the desired one. Okay, so if you see the relationship, which very clearly says that your delta P mechanical minus delta P electrical times 1 upon ms will be my delta omega. So that is what the relation is all about. So how do you get into this block diagram? Because A, which is pi r square delta P max minus delta P electrical, which is omega I d upon dt of delta omega, which is m times d delta omega upon dt. Now further, expanding this equation, you will come to know the generator, which is being actually represented in mathematical form, because these mathematical representations will help you to carry out certain analysis or derive certain expressions for your real-time analysis. Okay, so that means if I do a computing program, for an example, so I cannot take my physical machine and say that this is the device you measure the speed. Okay, so you have to represent each and every variable or component in a power system in the mathematical form. Okay, before we create the whole control loop. Now similarly, we'll try to model the load. Okay, mathematically. So how do we do that? So when you talk about change in load, that is delta P electrical, we say change in electrical power. So there are two different components who decides the change in power. So because we behave differently, so one component which is non-frequency sensitive load changes. So that means there are few load changes. They are not frequency sensitive, okay, non-frequency sensitive we call it. So irrespective of frequency, they will disturb. Now one more component which is frequency sensitive load changes. So that means if you change the load, then the frequency will be disturbed. Okay, so because of that, the change in P, delta P, which is given as two different components. One is delta PL, direct load change, and the other one is actually frequency dependent, which is d delta omega. All right. So if you see the equation, it is just compared to the previous diagram that I've given to you. What will happen? The delta P mechanical, delta P electrical, and the P load, and the delta omega is in its place, but you could see that the delta P electrical will also add another component, which is d times of delta omega will now be injected in the place of actually delta P electrical. So instead of delta P electrical, this equation, as you could see, which is being replaced by these two components. Okay, so from the above equation, delta P electrical is being replaced by delta P load and d delta omega. Hence, my original block diagram is now being replaced with this. Now, I can make further simpler, because as you could see, it is 1 upon ms, and then there is d. You can combine these two blocks, and by combining, you can get 1 upon ms minus d. So my new block diagram now will be delta P mechanical with a positive input and with a negative feedback of delta PL, and the output is delta omega with a block of 1 upon ms minus t. So this is what the current position. Further, we will make it more clearer with other variables. Now, if I go back to my generator model now, so because it may so happen that you may have a power plant with many generators, all right? So now, assuming there are n number of generators placed in a power system, so you could see the input may come from, because there is a change in load, I like to meet through n number of machines. Okay, so the mechanical power input from the machine 1, machine 2 and machine n may contribute to achieve your load change. So if that is the case, then the diagram is now being extended to this form where you have delta P mechanical from generator 1, 2 and from n, and delta PL was there as it is, and then you have D equivalent, because when you have many machines, one machine means 1D. But if there are n number of machines, then you have n Ds. So you have to have D equivalent, and then you can have 1 upon M equivalent minus S into S, and this delta omega. So it is now important for a multi-turbine generator model. It is as same as my single machine, excluding the change in mechanical power inputs has to be different, and also the D and M need to be not based on a single machine, but it is multi-machine based, so you need to determine what is D equivalent and M equivalent for n number of machines. Now, if you see that way, then further you can change the system to a simpler diagram. So the delta P mechanical, which is available to you. So this is basically a model where you can say, so let us fix it here. Okay, so you have actually delta P mechanical, and then you have delta PL, then 1 upon ms plus D, and then your delta omega. Now we need to understand from where I am getting actually delta P mechanical, who is providing this, okay? So they are coming from a valve, okay? They are coming from a valve. So I can have delta P from a valve with a constant 1 upon 1 plus ST. I will explain actually those variables, and then you get your delta P mechanical, and then the rest of the portion remain same. So this section is exactly similar that you have already discussed. So this could be either for a single machine or it could be n machine system, but the structure of the block diagram of the generator remain same, excluding few of the variables that need to be replaced from time to time. So let us move to what is governor model with droop speed. Okay, so governor model, actually, as you all know, this is quite interesting. So for the governor model, first of all, this section we have already discussed, but the governor model will help me to understand how this mechanical power that is being injected. So what we do basically, we provide steam for the machine to run, and that get into the steam ball, and that rotates my rotating shaft, and then we can measure the speed, all right, and then you can feedback mechanism to the valve. So this is what my delta P valve, which is appearing here, which decides that how much steam has to be given to the steam valve to rotate the prime mover so that my required frequency is being met. Okay, so this is very critical. I request everyone to concentrate and focus here. So we do have a load reference point here, am I right? And then this is basically your omega reference, which is let's say we like to operate at 50 hertz for an example, or maybe 60 hertz, whatever it is. So, and you could experience some change in delta, and that delta being actually managed, and further feedback mechanism has gone to my steam valve, so that in due course of time the frequency can easily be achieved. So this is the overall governor model actually with speed droop. And what is speed droop? Try to understand. In speed droop characteristic is very simple, where it talks about your frequency versus power. Okay, frequency versus the output. Now one thing is very clear, if the load is high, okay, and if you are drawing maximum power, then your frequency is expected to drop. Okay, how do I explain? If you are riding a cycle, and if you allow your friend to sit or ride along with you, or someone jumps into your back seat, okay, then the load become very, very high. Then it is expected that you slow down, the speed will slow down, okay. So similarly, when the load increases, probably the frequency drops, okay. So similarly, when the load is low, if the weight reduces, then you ride faster. When the weight is more, then you ride slower. So if that is the true characteristic to me, and this is basically the power versus frequency changes. And you could see that for different power variation, that is, if you move from P1 to P1 dash, okay, so that means there is increase in power. So that has forced my frequency to drop from this level to this level. So this is the mechanism you to understand. Now what happens, the droop characteristic will be different for different machines, for different systems. So unit 1, you could see by increasing this much of power, the frequency drop this way, and the other one actually by changing the power, actually the frequency drop. But one thing is very important, if you fix the frequency drop remain constant in both the machines, then the change in power, okay, need not be same. They need not be same for two different. Okay? Either if you fix the power, where power variation same, then your frequency variation become different. And if you fix the frequency, then your power variation will be different. If there are two different machines or two different systems. Now we'll get into the model of generation, governor, prime mover, and rotating inertia. So now it is a club system. So this portion we have already seen, where there is a mechanical power input, and we have P load, and this equation is known, and delta omega. Now what we are doing actually, because this prime mover up to the P valve we have seen, now slowly we merge the first section to the second section. Now we are adding the governor one actually, and finally you could see the overall block diagram of the whole system is captured starting from the load reference point. So you have to have the load reference point, and then whatever the practical delta omega you get, that need to be reversed as a feedback mechanism to know whether you further need to change your valve or change your speed and then change your frequency. So this is keep on changing. So every second the frequencies keep on oscillating, the valve is keep on changing its injection, and the prime mover is keep on moving in a different way. And hence we always try to reduce the gap of delta omega. So the delta omega is expected to be 0 in a practical circumstances, where whatever the desired frequency you are able to achieve by managing all these changes. Now if you solve this block diagram, so what you'll find that the delta omega, which is delta PL, just a minute, yeah, that is delta PL upon 1 upon R1 plus 1 upon R2 plus 1 upon Rn plus D. Now, why there are R1, R2, Rn? So probably the question could be because of different machines will experience different Rs. So this is my actually generalized equation. If you go for tie line model, actually, tie line model, I already told you that you have two different areas and connected through a tie line. And this is one area you can control your change in load, okay? If there is load change, you know how to manage. This is another area, if there is load change, you know how to manage. Okay, both the machines you can manage. But if there is a tie line, and you are committed to allow some X megawatt of power to flow, so then this X megawatt power become a load to this generator and become an injection to this generator, okay. So now because there is a tie line, due to tie line, now each modeling of area 1 and area 2 become different. So whatever the modeling we have done in the past will change if there is a tie line attached to that area. Okay, if there is no tie line, you are perfect. But if there is a tie line, then that variation need to be accommodated. So what is tie line? Power flow, which is 1 upon X tie theta 1 minus theta 2 because it decides based on the angle variation between two terminals, you will have the power flows. The flow model using linear power flow model can be also mentioned as p-type flow, which is 1 upon x tie delta theta 1 minus delta theta 2. Also can be written as p-type flow, which is t upon s delta omega 1 minus delta omega 2. So the power flow in a tie line depends on the frequencies of both the area 1 as well as 2. Now again, the same system I like to model with the tie line. So if you look at this diagram very carefully, so what we have done, so this is what the tie line power flow, which has been mentioned, delta p tie, the change in tie line power flow, and this is what the exchange that takes place, the interconnection between two areas. So this is my one area, and this is area 1, this is area 2, and there is a tie line. So absolutely same system with two different R1s, R1 and R2, different variables. And there is a load connected to first line, first area, which is delta PL1. For the area 2, this is delta PL2, but they are also interconnected. So what has happened now? Now the change in load in the area 1, change in load in the area 2, and the change in tie line flow, they are now interconnected. Okay. Now, how does the frequency response to load changes? I've already discussed, but I'm repeating it again. So, what exactly happens if there is a load change? There is a load, there is a step change in my load. So, when there is a step change in load, so you could see the frequency that start dropping. So, load increased, the frequency drops. But this happens actually if there is no governor action. Okay, that means load increases, this drops. Imagine that you are riding a cycle, someone joined you or tried to capture this back seat of yours, and the load increases, so the speed reduces. But if there is a mechanism to increase the speed based on the load increases, then probably your speed become constant even though there is a variation in load. So that exactly happens in your machine, where even though the load changes, the frequency is expected to drop, but it not drop continuously if you can accommodate governor action to that. Okay, so you could see in the first case it drops, but in the second case it drops, but finally it controlled to the desired frequency. And the change in frequency delta omega is given by minus delta PL upon 1 upon R1 plus 1 upon R2 plus D1 plus D2. Now, what do you understand by supplementary control? Because this is, don't get confused here, because this is for USA model. You can also write it down 50 Hertz for rest of the country, or maybe for India for an example. All right. So supplementary control is necessary to drive frequency back to normal. So if the frequency drops, then you have to bring back to normal. So that type of additional control is known as supplementary control. So you could see this segment, which is responsible for bringing back the frequency change due to load changes. Now, there are a few basic rules that we follow in case of tie line control. So these are standard regulations. What happens? There is load change, delta PL1 is positive and delta PL2 is 0. Means there is no change in load in my area 2. So this is my area 1, this is my area 2, or you can say this is my machine 1 and this is my machine 2. So if there is no change in load in my machine 2, but there is change in load in my machine 1, that shows that increase P generation in system 1. So because there is no change in the second system, okay, there is no change, so don't disturb. If there is a change in load in your area 1, so you have to increase the generation of the area 1 to meet the load. Similarly, if there is a reduction in load in your area 1, no change in area 2, then you have to decrease the generation in that system. Okay, the same thing applicable to your area 2 also. And subject to, you can also imagine that the delta omega, which is negative, and delta P net, which is negative, One segment I will clearly explain to you so that you don't have carry any confusion. Now let's say when delta PL1 is positive, okay, so that means there is a frequency drop basically, load increase of frequency. So that means delta omega becomes negative, and the delta P net interchange, which is negative. All right. So because it's a load increased, okay, the load increased here, so that means this flow will be negative because you cannot beat it out, and there is no change here. And to balance the system, now you have to increase the generation of the system. The similar rule is applicable to different, whether increase and decrease for both area 1 as well as area 2. Now, what is area control error? Because that is an important factor, because when there are two different areas, so there is an area control error which has been calculated for area 1 as well as area 2. So AC1 is nothing but minus delta P net interchange of the first area minus B1 of delta omega. Similarly, the area control error of the area 2 is minus delta P net interchange of the area 2 minus B2 delta omega. Now, let us move to a very important logic known as generator allocation using participation factor. So, first of all, I'll just give you the mathematical equation, then I'll try to explain you what it is. So, what it talks about, first of all, try to understand Pi dash is the new desired output from unit 1. There is a unit, you expect something need to be extracted, that is Pi dash, which is new desired output from unit 1. And then what is Pi base? Is the base point generation from unit 1. Means there is a generator which is generating, let's say, X megawatt of power, but you desired it to give you X plus delta X. Okay, so the generator is giving you a power of, let's say, 100 megawatt, but you desire to have 110 or you desire to have 90. Okay, so there is a base point and there is a desire. The delta P total is change in total generation, okay, that you need to calculate, and P unit total is the new total generation, and PFI is the participation factor of unit 1. Means if you have a large system connected to n number of systems, means many generators contribute to the required load. If there is a load change by X percentage, how that X percentage change in load is being supplied by n number of generators is known as participation factor. Delta P total, that means the change in power total, is nothing but my PU new total minus all the generators Pi base, that will give me the change in delta P. So you have a total power minus all the base values of the generators. If there is a difference, that will tell me how much delta P required in larger system. And now for a particular unit, Pi dash means unit number i's desired will be calculated based on the Pi base plus the participation factor PFI multiplied by the delta P total. So once again repeating it, because this is a very important concept. So first of all, you know the total power requirement, and you know how much all the generators are providing at this point of time. So if your desired power is increasing, the new total, so there is a gap between what you require and what is available to you. So from there you will calculate what is delta P total. Now you know how much change the system is now experiencing, and there are n number of units. I wish to know what is the challenge with my ith unit. So the ith unit output will be the ith unit's base value plus the participation factor multiplied by the total change in power of the whole system. Okay, I hope you understood thoroughly now. So one challenge here, how do you calculate PFI? That I haven't told, so probably it will be slowly clear. So please rethink. You need to know the PFI of each unit to calculate for a given change how much desired power can be achieved by a given system. Okay. Now, one more important concept, which is generator control loop, which is, as I told you, is desired output that need to be managed because you have the load set points, and the desired outputs can be achieved for any system, and there could be 1 unit, 2 units, and n units. So there is a closed loop mechanism among all the generators to achieve the desired output from n number of systems. Finally, there is one important point known as AGC calculations, and that also can easily be calculated. So this is my measured frequency, and this is the standard frequency that I want to have, and there is a change in frequency, that is delta f, and that will lead to the bias factor, and probably through telemetry mechanism you can understand the tie line flow, and that will let me know the actual interchange and the schedule interchange, and that will help me to understand what is delta P. And based on B delta F and delta P net, you can calculate what is ACE that I have already discussed in my previous slides. So this is what you see. So what is ACE? Is my delta P net minus B delta omega. So if you look into this equation, so ACE is nothing but minus delta P net minus B delta F. And the larger AGC system, if you look very carefully, it will look like this. The whole system, what we have already discussed now, this is the system we have actually, and these are the mechanisms where you get all the control logic data for overall control of a large system. Now, there are a few features of AGC. It assists action, move more unit to speed up control of AC. Filtering AC, don't try to follow random noise. Telemetry failure logic, don't take wrong actions when telemetry fails. Unit control detection, monitor generators to be sure they are responding control units. Ramp control, control rate of unit ramping. Rate limiting, keep unit changes within its rate limit. Unit control modes, example are manual, base load, and regular. Now, NERC control performance standards, this is being defined like, for a given situation, up to what extent we can tolerate the deviations. Now, let's say you have n number of systems, they are a tie line control. If one misbehaves, that will impact the whole system. Okay, so you have to be very careful and follow the guidelines. For example, if you remember, if someone keep on consuming energy in a particular state, which has been tie line with, let's say, another state, let's say Rajasthan and Uttarakhand, they are connected, and one state is keep on drawing power, and if there is a tie line, the power will go from the other state to, let's say, the Uttarakhand consume more power, then all the power from Rajasthan will move to Uttarakhand, and that will disturb the whole mechanism of Rajasthan state. Okay, so you have to be because when you experience more load through tie line, means your frequencies keep on dropping. Okay, and hence you are extracting power from others. So you cannot perhaps do that to disturb another system which has been controlled through a tie line. Okay, so we all have to respect our frequency and manage our own required load energy system so that the tie line commitment can be met. So if you see the first controlled performance standard, CSP1, which talks about ABG period AC upon minus 10 BI times delta F1 must be less than or equal to epsilon 1 square, where AC is 1 minute of AC for the minute indexed as I, B is the average frequency bias in effect over that minute in a particular point, and delta F1 is the 1 minute average of the interconnection frequency error, and epsilon 1 square is the constant determined by each interconnection to meet a specified frequency bound. Why we do all these things? To make sure a stable system to operate when everyone is integrated. Now the CSP2, which is AVG 10 minutes, okay, previous one is 1 minute story, now it is 10 minute story, AC less than or equal to L10. That means AC for at least 90% of the 10-minute period during a calendar month, that is the maximum oscillation or variation can be allowed. So L10, which is 1.65 epsilon 10 under root minus 10 BI square, okay, and 10 BI times minus 10 B1. So epsilon 10 is the RMS of the 10-minute average frequency error over a given year and is the same for all control areas in the same for all control areas in the interconnection. Means what we expect that you can certainly face some practical challenges, but those challenges need not be so frequent. Okay, so otherwise you'll be penalized by the central authorities very seriously. Now, by doing that, what we are achieving, if you have not control performance standards, it allows control areas to minimize by allowing maximum allowance for value of A. So if your area control error is perfect, then you will be given allowances. The larger allowed AC, the less do generation unit need to reverse and maneuver. Now lower maneuvering means less bearant on valve gear and control. Means if you pressurize your generators to behave in a ramp way, that suddenly you give me 100 megawatt, suddenly you reduce your generation by another 50 megawatt. This is not practically acceptable, though theoretically it is true. So we don't allow, based on this ramping capability, only a minor change is acceptable. So to do that, to make my machines robust, to make my system operational and reliable, we can allow a certain variation in my AC, and that is governed by certain standards. So with this note, we come to an end of this section. Thank you very much for your kind attention.